Hi, everyone. It's my pleasure to introduce our speaker for today. Thank you for coming to this very interesting presentation on tDCS, and more exactly a mechanistically informed tDCS intervention to restore behavioral responsiveness in disorder of consciousness, presented by Davinia Fernández Espejo. Davinia is a professor in neuropsychology and clinical neuroscience at the School of Psychology, University of Birmingham, and principal investigator at the Center of Human Brain Health. She obtained her PhD in biomedicine from the University in Barcelona in collaboration with the University of Cambridge before moving to Western University as a postdoctoral fellow in 2011. Davinia, thank you so much for coming, and we're all looking forward about you talking about tDCS and its brain mechanism of recovery. The floor is yours.
Thank you, Caroline. Thank you for the introduction, and thank you and all for the invitation. It's really nice to be here. I've seen some surprised faces here and names that of people that I've known for a while. So hello, I'll send an email later. It's really nice to reconnect. I'm going to try to share the slides and see if that works, and then I'll get going. Continue to share. Can you see the slides now? Yeah, I see people nodding. Fantastic. Okay, so as Caroline said, I'm going to be talking about some work that we've done in the lab to try to develop a tDCS intervention for disorders of consciousness. So before I get into that, I wanted to talk to you a little bit about what we do in the lab. So we have several lines. As Caroline said as well, we're based at the University of Birmingham in the UK, and we're currently working on biomarkers, both for disorders of consciousness and for mild TBI. We do quite a lot of work in terms of interventions using several non-invasive brain stimulation techniques, including tDCS, ultrasound, vagus nerve stimulation, both for DOC and for pediatric patients with acquired brain injury. And we've done quite a lot of work as well with healthy volunteers and patients in terms of the neural correlates of consciousness. So specifically, the stuff that I'm going to talk about today is around interventions in DOC. So this is just an outline, so I'm going to talk about a little bit about DOC. I wasn't sure how familiar the kind of broader audience would be about DOC, so I'll do a bit of introduction. Many of you are super familiar with these, but hopefully you'll bring us all on the same page. I'll talk a bit about cognitive motor dissociation and then the steps that we in the lab have taken for developing the intervention. Okay, I probably don't need to explain these in too much detail. It's just the idea that when we talk about consciousness, we have to consider two dimensions, both the level of consciousness and the content of consciousness, also referred to as wakefulness and awareness. And these are important because they tend to come together in kind of healthy states of consciousness, from deep sleep, light sleep, conscious wakefulness, etc. But then we have disorders of consciousness, such as the vegetative state, now called unresponsive wakefulness syndrome, where we have a dissociation, whereby the level of consciousness is preserved, but the content of consciousness is presumed to be absent. Level of consciousness is quite easy. It's very easy to tell whether somebody's awake or asleep. We can just look at them, but also we can measure that objectively with techniques such as EEG. The content of consciousness is a little bit tricky. And something I like to think about sometimes when we talk about consciousness, because I think it helps us understand a little, or put into context a bit better, the assumptions that we're making when diagnosing our patients, is to think about what it means to be conscious. What do we consider consciousness to be? And of course, there's a million definitions. We don't agree about which one is the one that we're all happy with. But from a very intuitive point of view, if you were to think about the person on this slide sitting on the hill, looking at the beautiful landscape, her senses are going to be registering the information about the temperature, about what they can see, what they can hear, etc. But on top of that, this person is going to be having an experience that is unique to them and unique to this moment. They might be having thoughts about what this landscape reminds her of. They might be having some perceptual sensations about the temperature that they're feeling. They might be feeling a bit hungry. They might be thinking about what we're doing later. And even if this person was to come back again to that same spot and in the same weather condition, the experience that she would have would be different because it would be a new situation in which she would bring all the new thoughts, perhaps the memories about the last time she was there, etc. And this, in a very intuitive point of view, this ability to have subjective experiences that go beyond perceiving the stimuli for the environment is what we consider consciousness to be. You might have heard some people talk about this kind of what it feels like to be you. There's a very specific sense of agency, sense of self that we all have. And this is also something that we talk about when we talk about consciousness. And the reason why I think this is important to kind of raise is not so we kind of go into debates about kind of theoretical descriptions of consciousness, but because this is what we assume is lost in a patient when we diagnose them as unresponsive vagal syndrome or vegetative state. The issue with this is that it's really, really difficult to measure consciousness, and I have no way to tell anything about your subjective experiences right now unless you tell me about it. And if you can't tell me about it, then I have no way to access it. And this is what makes it so hard to tell whether a particular patient is or isn't conscious. And what we do instead is we make a judgment based on their behavior. And if you're into science fiction, you might recognize this picture. But basically, this is kind of to convey the idea that at the end of the day, the only way to know whether somebody is conscious or something, in the case of this picture, is to have an interaction with them and make an informed assessment of what their behavior looks like and whether their behavior corresponds to what we consider a conscious being to be. In the case of patients who might not be able to communicate with us the way that we would, then this is typically done by using command following as a proxy. And I made that as a kind of a little bit of a funny description of what it would like. But basically, we need patients to perform to the commands that we give them for us to be able to assume or conclude that the patient is conscious. Just real quick, I'm not going to wait on these, but this is kind of the profile of the patients that we see. Typical, so I only work with adults who have had a severe brain injury, are in a coma for a little bit, come out of the coma, and they go into these conditions that in the UK, we define as prolonged disorders of consciousness, or PDOC. In other countries, we tend to use only the DOC label. So these make up for 30% of traumatic brain injury survivors. And again, what we're saying here is that in the case of the vegetative state, they have a full or partial lack of awareness. So if you go back to the picture, we're assuming that they're not able to do that. They're not able to have experiences of the external world or themselves. But in reality, that's what we assume. But what we are actually testing is that there is a full or partial lack of evidence of awareness. We cannot tell that they're aware. So therefore, we assume it to be unaware. For those of you who are familiar with this literature, I probably don't need to explain this paper. The situation changed dramatically in 2006 when a team led by Adrian Owen in Cambridge demonstrated that some of these patients were actually aware and capable to show it if the command following, the simple commands that we're asking them to do, don't rely on them being able to perform a physical action, an external action, such as raise your hand, open your eyes, etc. But instead, we ask them to do something in the scanner. The typical task that was used and has been used a lot in the literature is to ask them to play tennis. There's nothing special about tennis. It's just an easy way to ask somebody to imagine they're swinging the hand back and forth. So in this case, this was a single case of one patient who, despite the diagnosis of vegetative state at the time, she was able to follow commands if you ask them to imagine playing tennis and respond to commands rather than to actually move the hand when it was necessary. And the same for the walking around the house. Now we talk about, at the time, we were talking about covert awareness, and we didn't quite have a label to define these. And nowadays, this is very well described and defined, and we talk about cognitive motor dissociation in these patients. You may know of this paper as well, really important paper that expanded the findings in the 2006 one, where now they tested and demonstrated these CMD in a larger group of patients, but they also were able to use this technique to communicate with patients who were asked to answer some yes/no questions, where they could imagine playing tennis to answer yes, and they could imagine walking around the house to answer no, or vice versa. So this was a really important paper because it tells us for it fully demonstrates that the behaviors that we're seeing in these patients are not automatic, but also that these patients retain a great deal of cognitive functioning so they can communicate using these sort of tasks. In this paper, they use factual questions. They ask about names of their parents, names of siblings, etc. In a further paper that we work on when I was working with Agent Owen in Canada many years ago, we tried to think whether we could turn these into something that we could use as a kind of very rudimentary cognitive assessment. So now we wanted to ask questions that we didn't know the answer for, that would help us understand a little bit better what it is like to be in this condition, and also ask patients about the wishes. So we only managed to do this in a couple of patients, but this is, I think, a very powerful example of what this means, because we had this one patient who had been in a vegetative state for 12 years after a car accident. This patient, we assessed them multiple times, and at no point he showed any behavioral evidence of being aware. So in that sense, the clinical diagnosis was correct. Yet when we put him in the scanner, he was able to play tennis consistently. So we asked him some questions following Monty's protocol in the slide before about factual things like names of family members, etc. And he could answer all of those correctly. So then at that point, we asked him some more interesting questions. So we tried to ask him whether he was oriented in time and space, with questions about the year and about whether he knew where he was. And we also which he answered correctly. And then we also asked some questions about people that had only been in his life in the time where he was in a vegetative state, and he could answer those correctly, demonstrated that he had formed new memories, that he had experiences of events that had happened while he was, for all extent and purposes, clinically in a non-responsive state. We also use these to ask some clinical questions and preferences for care. We're not in a position where we can ascertain capacity in these patients, obviously, so the questions were there was a low bar for the questions that we could ask. So we only ask questions around, things that they would like to watch on the telly, etc., and whether they were in any pain. So we managed to do these with a few patients who were diagnosed as in a vegetative state or unresponsive wakefulness syndrome, demonstrating that these patients have, as I said, a great deal of cognitive functioning, and also some experiences, some sense of being, some sense of what's going on around them in the period while they're in this condition, which is, at least for us, was really important. This is another really important paper that's come out recently. I can't remember if it was last year or the year before now, because we're in 2026, where we now know that actually 25% of patients who are diagnosed as being unresponsive are actually aware, and they can actually show it if you use some of these techniques. Tennis is one of them. There are other techniques, and this can be done with MRI, with EEG, and with other imaging methods. So 25% of them can do these, which I think is very, very, very striking. So what this tells us is when you're talking about the level of consciousness and the content of consciousness, this is not enough. And there's a third dimension that we need to consider, and it is really important when we're thinking about therapies, which is, and this is my rudimentary attempt to kind of represent this in some sort of meaningful way, which is the behavioural axis. So we need to think about the level of consciousness, the content of consciousness, but also the patient's ability to show these with an external behavior. And what I colored in green here would be us, who are behavioral, who are wakeful, and who are aware. And what you have here in pink is the CMD, which are patients who are also wakeful and aware, to some extent. But what's the problem here is not their awareness. The problem here is in the behavior, is in the fact that they're not responsive. And I think this is the particular dimension that we've tried to concentrate on when trying to think about therapies. I'm not going to talk a lot about this paper, but I just wanted to kind of make a small comment that actually only a small subset of patients can communicate. So, well, we know that 25% of patients have CMD, not 25% of patients can communicate. And actually, when you look at the data from behavioral assessments, this is also true. From patients who are MCS plus and can follow commands, a very, very tiny percentage would kind of move into the next stage when they can communicate and move out of this diagnostic criteria. So if you're interested about what might be going on in the brain of these patients, to explain why some people may or may not communicate and why being able to communicate and select between two potential candidate responses to produce that response is harder from a neural level, then you can look at Natalie's paper here and it might give you some hints. However, even when not all patients can communicate, these 25% of patients who can do tasks like tennis can understand language, have enough working memory to be able to retain the instructions of the task for the 5 and a bit minutes that takes to complete this task. They have volition, they have to decide to do these. If I put any of you in the scanner and I play the instructions of the task and you're there thinking like, whatever, I'm not going to do anything, I don't see anything in your brain. So you need to want to do it and you need to actually put effort into it. They have attention to be able not just to kind of pay attention to the instructions at the beginning, but to kind of be able to maintain the attention in the task. So even when we don't have any details about or any formal neuropsychological workup of what these patients look like, we can infer that there's a certain level of most neuropsychological faculties, if you like, that is preserved in these patients. Okay, just quickly, in terms of when you're thinking, that's fantastic. So if we see a patient with CMD, does it mean that it's going to get better? Well, not really. So if you see this acutely, and there's some nice evidence coming from Brian Edler's lab, it has some prognostic values. If you see it in the ICU, the patients who have CMD early on are more likely to do well as compared to the ones who don't. But if you see this in the chronic stages, then it doesn't tend to predict a good outcome. So, and if you think about the patient that I just talked about, he had been in this condition for 12 years. I don't know whether he was conscious for the full 12 years, because obviously he hadn't had an MRI until we kind of got him into the research program, but he could well be. And he was in this condition until he passed away a few years ago. This is going to be different across countries, but in the UK, this is the guidelines that apply in terms of clinical care for these patients, as set by the Royal College of Physicians. And there's some very critical differences in the guidelines between the UK and Europe and the States. So here, these patients do not qualify for any therapeutic intervention. So it is considered that there's not enough evidence to support any interventions, and the pathway of care for these patients tends to be management of disability. So these patients would go into a rehab unit in which the focus, in the kind of subacute stage, in which the focus is to perform an assessment of the needs and a plan for the management of the disability before the patient moves into a long-term care facility. So for me, who I had been working ever since my early PhD days and trying kind of to diagnose and uncover covert functioning in these patients from one stage to another, knowing that there was nothing we can do to actually help them was extremely frustrating and quite heartbreaking, to be honest. So the way we went about it was, okay, so if we want to do something that works in these patients, there's several ways we can do this. We can try a bunch of things, and if one of them works, then fantastic. And this is a good way to try things in these patients. Or we can try to go to these in a mechanistic, hypothesis-driven way, in which I try to see what can I target, how can I target it, and then kind of try to develop the intervention from that point of view. So the first thing that I wanted to do is, what's wrong here? What's happening? What is causing this behavior in patients who are conscious but they can't show it? So there's been quite a few different attempts to try to establish the neural basis of cognitive motor dissociation. This is an EEG paper published by Srivastanu quite a while ago now, where they were looking at kind of brain networks. I'm not an EEG expert, so I'm not going to pretend I'm not going to try to explain these in great detail, but what you can see here is a measure of the connectivity in the brain as indexed by certain EEG metrics related to oscillation. So what you can see is that in the healthy volunteer on the right, you have a brain that is highly interconnected. Different bits of the brain are talking to each other in a quite a complex way. When you have a patient in a vegetative state or unresponsive wakefulness syndrome, you see that there might be some small islands of communication, but typically the communication across different bits of the brain is not there. And what they saw quite strikingly is that when you have patients who are tennis positives, these covertly aware patients, you see a pattern of connectivity that resembles quite closely what we see in the healthy volunteers. This is not the only paper that has shown something like this. In a more recent paper that involves a collaboration across multiple centers, combining a large group of patients, what we're looking now is at fMRI, resting state fMRI, in a dynamic way, when you're looking at the different patterns of brain communication, if you like, that our brains can get into over a period of time. And this tends to be considered, kind of name that we use is brain states. So there are different brain states that all our brains entertain at different periods of time. Some of them are more complex than others. And what we could see in this paper is that the patterns that are more typically related to unresponsive wakeful state or syndrome, which is this pattern 4, which is a pattern that had very little connectivity between distal parts of the brain. I guess this is a good way to put it in an intuitive way, was much more represented in patients who were truly vegetative or UWS, and not in those who were tennis positive, covertly aware, CMD, whatever you want to call them. So these things collectively, and I chosen to pick these two papers, but there are many other papers that kind of speak in this direction, that actually the resting state activity in patients who are CMD kind of is closer to what we see in MCS and in healthy controls as compared to what we see in truly UWS patients. Now, these might explain why they are aware. It might kind of tell us that the brain is capable of complex behaviors, but still doesn't explain why they are unresponsive. So you may want to, I'm not going to talk a lot about this paper for the sake of time and kind of move on into the intervention, but this is a recent paper that beautifully looks at these, comparing patterns of damage between CMD and non-CMD patients in a very large, for this group of patients, very large sample. So I would recommend you to read it in you're interested in these. But I think it also, in the comparison between CMD and not CMD, we're comparing the pink square here with the red square here. And the difference for these two is the level of consciousness, the content of consciousness, the awareness, the capacity of being or not being aware. And I think we're still not very well understood is this, the difference between the pink and the green, which is us. So forget about awareness, forget about consciousness. What makes us more responsive? What makes you able to move to command? And this is what we would try to do. So we kind of talk about, why can't these patients play tennis? Now, you might think, if you're not familiar with these patients, maybe they can't move. But those of you who work with these patients, they can move, and they do move, in this kind of, and it makes our life hard when we're kind of trying to analyze the data. So it's not a paralysis. What specifically, and if you want to frame these in a more kind of scientific way, the question would be, how is it possible that these patients can imagine motor responses in response to commands or external cues, but they are not able to execute them when, in terms of the motor output, they're not paralyzed, they're able to move their hands, they're able to move their limbs, to different extents, depending on the damage, obviously, but this is not what's explaining it. So we have a situation in which the motor planning is intact and we see activity in the supplementary motor area that is related to this kind of building of plans to kind of execute a movement. In terms of peripherally, the patients are not paralyzed. So the problem has to be in the ability to voluntarily control motor responses. So how do we turn those motor plans that we can build in the SMA and that we can detect in the scanner when we're looking at the tennis activation? Can we turn that into orders to M1 that are then sent to the limbs for people to move? So we did this paper a while ago. This is a friend of mine posing for the photo rather than a patient. So that's why you can see her face quite clearly. Had this construction in the scanner when we had people elevated so they could have a visual of the objects that we presented in front of them. We had a tennis ball just because I thought it was fun to have an actual tennis ball in there. The MRI was in pitch black. There was some lights. This was to avoid visual feedback of the executed movement as compared to the imagined movement. And when we asked this set of healthy people at this point to do was to, when we were playing certain instructions in the through the speakers, there would be a little flash of light that would illuminate the tennis ball, and the instruction was either to move the hand and try to hit the tennis ball or to stay still and imagine that they were doing that movement. So what we're trying to get at here is what is the difference from the point of view of fMRI and what we can detect between imagined command following and executed behavioral command following. Okay, so we analyze this data with something called dynamic causal modeling that I'm not going to get into a lot of detail, but basically allows you to look at causal relationships between different brain areas and their activity. And the important thing here is that from the point of view of the brain activation, we saw that the activity was relatively similar between moving and imagining to move. But from the point of view of the causal relationship between the different regions, for you to be able to move, you need to command voluntarily. You need the thalamus to get excited and send an excitatory output to your primary motor cortex or M1, which you can see here on the bottom right. So this needs to happen if you want to be able to move to command, but it's not necessary if you want to be able to only imagine a command but not produce an external behavior. This was in healthy volunteers, and it kind of gave us an understanding of the difference between these two tasks that we use for the diagnosis of these patients, being the covert one or the overt one. So then what we did is we look at the patient that I've told you about, who had CMD, who was from the point of view of the clinical assessment, entirely unresponsive, but who could do tennis, who could communicate consistently. Every time we put him in the scanner, he was able to do that. And we then use a technique called diffusion tensor imaging that allows us to reconstruct white matter fibers connecting different bits of the brain. And we went to this in a hypothesis-driven way. So we know that the fibers connecting thalamus and M1 are important from the point of view of the need to be able to transport some excitatory input to M1 that then would send the signal to your arm to move to whatever part of your body you want to move. So we're going to look at the damage here. And then we had this patient and we had a second patient who had a very, very similar history, very similar level of structural damage when you looked at the brain. But this patient had emerged from a minimally conscious state. So she was able to follow commands and communicate behaviorally. And what we saw was that for the patient one on CMD, there was a specific damage that was above and beyond the general damage to the white matter to the brain that was affecting specifically the fibers that you see in red, which are the fibers that connect M1 thalamus to M1 or vice versa, because with DTI we can't tell the direction of the fibers. So, but it was not affecting the fibers connecting thalamus with SMA, for example, as a control fiber. And this damage was not present in the second patient who was behavioral, who was able to perform these behaviors behaviorally, or externally. So what this tells us, or gives us, is a potential candidate for a target that explains why patients might be able to imagine motor behavior in response to an external cue, but not able to execute it with an action that we can see in assessments such as the CRS, etc., that we may use for diagnostic purposes. This is 2 patients, so obviously it's a very small amount of evidence, but we've run these with a larger study that we published few years later, in which we look at these fibers as well. And again, we saw that the level of integrity in these fibers is related to the level of which patients are responsive or not, but not the level to which patients are conscious or not. So these are fibers, unsurprisingly, because they're part of the motor network, that are the damage in these fibers is going to predict the level to which a patient is responsive from a kind of motor external behavioral point of view. In this paper, we also saw that there was other pathways related to conversations between the cerebellum and the thalamus that might be interesting, but I'm not gonna get into much detail about that because it takes me into a bit of a detour. But there's some interesting things as well in terms of potential actions into the cerebellum that could be beneficial for these patients. Okay, so I'm not gonna say this is what explains for sure, the deficits that we see in these patients, but is a good working hypothesis for which we have evidence that it might be at least a potential mechanism to explain the lack of external responses in these CMD patients. So as far as I'm concerned, we have potential target. So the second thing is, okay, now we have a target, now what we do with it? And one of the main things that we can think is, let's just do DBS. And obviously there's these trials of DBS that have tried this from a different point of view and affecting different thalamic nuclei. The thalamus is an extremely complex structure. But obviously we have to consider safety and practical aspects that would facilitate the translation to clinical use. In the UK in particular, it would be really hard to get a DBS trial approved at the minute for these patients. So we have to be looking at things that can be done non-invasively and things that can be deployed at scale. So one of the things that we thought about here is, okay, because I'm saying that there's structural damage to the thalamocortical circuits that is explaining this functional dysfunction, if you want, that would lead to reduced responsiveness in these patients. But we can still reconstruct the fibers, so there's still a path there. It's just there is damage. So the idea is, can we compensate? Can we stimulate the network to kind of put a little bit more energy into the system that can bring the patient above threshold to be able to produce these behaviors in response to command? And a way that we and many others have gone about it is with tDCS. tDCS is very noisy and this is a challenging technique to use, but it's also very safe and very practical and very kind of suitable for delivery at scale, particularly in contexts like ours, where patients are scattered around the country, not necessarily in specialized centers. So for those of you who don't know about tDCS, this is a very simple, it's more complex versions, but the one that we're using is a very simple anode and cathode that we put on the head, delivers an electrical current that generates an electrical field on the surface of the scalp. Some of that goes into the brain and alters the excitability of the neurons in the kind of target area, depending on where you set up your electrodes. It's cheap, it's portable, it's easily delivered, people tolerate it really well, and there's no serious adverse events. It's being used in many applications across different conditions, and it seems to work really well sometimes and not well at all some of the times that we're trying to figure out why it might be. So obviously there all the groups that are publishing extensively on tDCS, or who's here on the call, has been driving the field for many years, and she's published amazing work in this area, and some of the early trials kind of providing the rest of us some confidence that actually tDCS is not a crazy approach to have, because it seems to have effectiveness in some patients, and I've put here a couple of examples of particularly influential papers from back in the day when we were all starting to think about these, that kind of set the direction for the field. So something that we've done slightly different here is that in many of these papers, not all, but in many of these studies, the focus tends to be on rehabilitating the awareness, kind of making people more aware. And as I said before, we're kind of taking a slightly different approach. It's like trying to make people more responsive and trying to attack this kind of motor behavior instead. So you might be thinking, wait a minute, but you just say that the important thing here is you need the thalamus to kind of get a little bit active and say something to the cortex for these patients to actually be able to move. But tDCS has a kind of surface sort of reach, and you would be absolutely correct. So the first question that we had here is if we were to stimulate the cortex, and particularly the primary motor cortex of M1, can we elicit some sort of network effect that can potentially reach the thalamus and change thalamocortical dynamics? And this was circa 2017 when we started to think about these, and there was very little evidence that could. There were some papers that showed that might be possible, but we didn't know. So what we tried to do is try to kind of address this question. So in terms of the kind of logic here, we have a target, we're going to alter thalamocortical dynamics. We have a tool that has shown some potential and that is safe, is practical. In one of the papers that I showed by our group, it was an at-home trial, which I think it was very, very important for our kind of setup as well, something that can be delivered by trained people who are not necessarily neuroscientists or clinicians. So the next thing was, okay, let's test the mechanism of action. Is this going to work? Is this going to alter the excitability of thalamocortical networks in the way that we need it to for these patients? So we first did this in the healthy brain. I find it much more straightforward to test things in healthy brains that work like brains first. So then I understand the parameters and I understand how things work. And then I move into the patients where everything is a little bit crazy and a little bit harder to understand. So we ran a set of studies. This is funded by the MRC, and this was a little bit of a roller coaster because COVID hit us in the middle of this. So we started this trial in late 2019. So some of the work that we had planned couldn't go ahead, but some of it did go ahead with a substantial amount of effort by the people that you see here in the slide. So what we get on to doing was, okay, so we're going to do tDCS in the MRI scanner, and we're going to measure changes to brain activity while we ask healthy people, in this case, to move the hand. And what we're trying to do here is, instead of tennis and swinging arms, which I had tried before, and it gives all sort of crazy artifacts in the scanner, because as soon as you start moving your hand, you move your shoulder, and then everything's a little bit problematic. So we went for a smaller movement, it's a thumb movement. And also talking to many clinicians, particularly around physiotherapy and OTs who work with these patients, they kind of thought that it's easier to rehabilitate a little bit of movement in the thumb as compared to other hands due to the kind of rigidity that we see in some of our patients. So we went for that. So what this looks like is I would have a healthy volunteer in the MRI scanner. You can see here from the back inside the kind of head coil connected to a tDCS machine that is MRI compatible. I would ask them to do a command following task, which now instead of tennis is every time you hear a beep, I want you to imagine you're moving your thumb. They also do a task where they have to move the thumb in response to beeps. We have a way to measure movement in the MRI as well. This was fun to set up. And then we also collect some resting states, some diffusion data, everything that we can possibly throw at them. And then we do 20 minutes of tDCS at rest in this case, where they're not asked to do anything and we just kind of deliver the simulation. We did it to the motor cortex with the montage you have here, and we also did a cerebellar one where we were kind of trying to inhibit the cerebellum, to kind of try to inhibit the action of the cerebellum into the thalamus. I'm not going to talk too much about that one. But if anybody's interested, just drop me an email and I can tell you all about it. So we did this, and then we registered, obviously, the brain activity both at rest, before, during, and after tDCS, but also during a command following task where the people were asked to move the thumb, in this case, before and after tDCS. And we also registered the movement. So the data is much more complex, but just to kind of concentrate on the important thing here, we analyze the data with dynamic causal modeling. Again, if you remember, we're looking at causal relationships between the activity of different regions of the brain with each other. So when we're stimulating M1, we did this in a way that everybody came through 3 sessions. One, we were doing a nodal stimulation, which is excitatory in principle. One, we were doing cathodal stimulation, which is inhibitory in principle, with many kind of caveats. And one where they did sham. So when I talk about what we found here, they're always in comparison with the other polarity and with sham. So we know that they're actually due by this particular polarity of simulation and not by some noise or placebo effect. So what we see here is that when healthy people were being stimulated over the primary motor cortex, we actually see an increase in excitatory activation in the thalamus, even when we're nowhere near the thalamus, and even when we look at the current in the kind of models of where we can see where the electrical field goes, it goes nowhere. You only have the surface map here, but we look at obviously the deep structures as well, and no significant amount of current reaches the thalamus. Everything stays in the surface, but when we ask people to move to command, the thalamus gets more activated, so in a kind of excitatory way, which was great as a proof of principle. And when we do cathodal stimulation of the cerebellum, we see an excitation coming from thalamus 2 and 1, which is fantastic as well. The important thing to know here is that the cerebellum at baseline has an inhibitory effect of the thalamus, and this is very well understood in the kind of motor neuroscience. So by inhibiting that inhibition that comes from the cerebellum, we may be able to increase the excitation going from the thalamus into M1. So I was really excited about this because we have a technique that, it can only reach the cortex, but we have evidence that even if the electricity itself only reaches the cortex, you can have a network effect and alter excitability somewhere else within the network, as long as the person is doing something that is relevant for that network, which in this case, if you remember that the healthy participants were moving the thumb. If you're interested about a little bit more nerdy aspects of this work, in here we look like a sliding window to see in real time what's happening to the connectivity in the motor network while we're stimulating. But it's also a little bit complex, and they're a little bit, it's a bit harder to kind of translate into recommendations for the implementation in patients. So, but I just wanted to put the paper in there if people are interested. Okay, so we do have a network effect, which is great. We can excite the thalamus, but we cannot, at least with M1 stimulation.
5 minutes, okay.
Yep. Yes, yeah. I'll wrap up soon. So we cannot do anything that that kind of reaches the. We didn't demonstrate that we could have thalamocortical activity increasing with this stimulation regime. So at that time, there was, and this is still the case, that we know that tDCS is state dependent. So depending on what you're doing while you're being stimulated, the effects might be one thing or another. So in the motor area, typically when you're doing tDCS, you ask people to move now and perform a motor task. Now, if our patients were able to perform a motor task, they wouldn't need this tDCS at all in the first place. So we have some anecdotal evidence that we haven't published because we didn't have enough patients, that when I move the hand of a patient for them in a passive way, we also engage these networks. So if I put a patient in the MRI scanner and move the hand for them, I see activity not just in the sensory regions, but also in motor regions and the thalamus. So that kind of gives us a bit of proof of principle that maybe if we do that passive stimulation, when we move patient's hand for them while we're delivering the stimulation, we may engage the motor network and enhance the effects that the tDCS might be having while we're delivering it. So this is what we did. And again, another crazy study in healthy volunteers when everybody came 15 times for 15 sessions of stimulation. Each week was a different polarity, one of them being sham. And we only did them one. Cerebellum was in the make, but COVID stopped us from being able to do that. In the scanner, they were being passively moved. We didn't have a therapist in the scanner moving them. We had a robot that was connected to the hand that was doing it in a very controlled way. And then what we had is that during the stimulation, so passive mobilization of the thumb during the stimulation, and then the same design where before and after the stimulation, they have to actually move the hand. And we did this over a period of 5 sessions per polarity, and we did MRIs on day 1 and day 5. So we have 6 MRIs per person and 15 sessions of stimulation, 5 per polarity. So what we see here is now, the nice thing is that in the first session, just with one session of tDCS, if now I'm moving your hand in even passively, now with a nodal stimulation, I can excite this connection between the thalamus and M1, and I can increase excitation on M1 that presumably then is going to help you move. So this worked beautifully, and this is enhanced even further if you do 5 sessions. So after 5 sessions, this enhancement of excitatory inputs between thalamus and M1 while you're trying to move your hand is enhanced further. So what this proves is that we can stimulate regions far away from our area of stimulation. We can increase excitation the way that we think is necessary to restore behavioral responsiveness in tasks like, behavioral command following. And then this is enhanced with 5 sessions as compared to just 1, but also present already with 1. So this was obviously really exciting, and I only have a couple of slides left, so I'll be quick. So, and then it proves that actually in the healthy brain this works, and it works the way that we need it to work for the patients. If you remember, I said that we had motor, motor tracking from the thumb of the healthy people as well, but obviously there's only so much better you can get at moving your thumb if you can already move your thumb. So we've analyzed that and we have some results there, but it's not super interesting. So the next step is obviously now to test it in the OC patients. And we've done this. And unfortunately, I'm not going to be able to tell you much about it because we're in the process of trying to get these published. So it's still quite, preliminary, but I have a sneak peek that hopefully makes you excited. And then I'm happy to talk to you about it another time when we have the data published. So we ran a trial called Raindrop. This was an enormous endeavour where we had a number of sites across the UK that ranged from NHS sites, which are within the kind of national health security, public healthcare network, can't come up with the right word now. We had centres that have charity status, and we have centres that work on the private healthcare section. So each of these sites cater for like different group of patients that come at different stages across the the clinical progression. So we have patients from kind of 3 months post-injury to a few years post-injury in our sample. This is what we did in healthy volunteers, and you might be thinking, those of you who work with patients might be thinking, you were not crazy enough to try this in patients. So the answer is yes, we were crazy enough to try this in patients, and I'm not sure I want to do that ever again. But it was really interesting and really cool. So we had patients again come for 5 sessions of each polarity, 2 MRIs, 1 on the first day, 1 on the last day for each of the weeks. Receiving tDCS over the primary motor cortex with the passive stimulation. Now here we didn't have a robot moving the patient's hand because the robot can't tell whether there's much resistance. So we have an actual therapist in the scanner leaning on the patient, moving the thumb while we were doing the stimulation and recording the brain activity. To make this even more fun, we added some EEG before and after. Some patients only did the EEG. Some patients did the full protocol with the MRI. And obviously we had daily pre and post CRSR assessments before and after stimulation on each of the at baseline and every day. So a huge amount of data that we are in the process of trying to make sense of. And just to give you an idea, so we only have 14 people. This was a feasibility proof of concept study. We're kind of trying to secure funding now for the larger efficacy trial. Mixed etiologies, mixed time post-injury, mixed diagnoses, so a fairly representative sample. And I just want to give you an example here of a patient. This is the kind of canonical, stereotypical patient that you hope to be able to rehabilitate, right? Young male, no comorbidities, TBI, less than a year post, probable CMD, behaviorally vegetative. And you can see here, when you look at the resting state activity before and after 5 days of a nodal stimulation, we can see, this refers to the alpha network, a much greater connectivity as compared to pre. And when we get the patient in the MRI and ask him to try to move his thumb, he could do it, he could imagine it because he was CMD, remember, but the activity after the stimulation is much stronger and it goes further away across the motor network. So what we see here is, at least in this case, we have a strengthening of the functional activity of the motor networks when we're asking this patient to perform commands behaviorally. You might not be surprised to know as well that in terms of the CRS, we could capture some changes in terms of the appearance of new behaviors that were not present without the stimulation. We have a bit of a mixed bag. We have the beautiful patients like this one and others for which it didn't work as well. Not unexpected. And we have the structural data now to try to see what the differences might be. So just to conclude, we have a mechanistic hypothesis to try to explain the lack of behavioral responses in CMD patients. We've tried to exploit this with tDCS and shown that we can modulate this mechanism, at least in healthy volunteers, have some early evidence that we can do so in DOC, and hopefully there'll be a paper showing this soon. And this kind of shows you hopefully an example about how neuroimaging can help developing and testing mechanistically informed interventions. So just to conclude, just want to thank patients and the families, collaborators, of which there's many, so I didn't want to put them all in here, just to kind of concentrate on this lab who's done the kind of all the hard work that I've shown you today. And thank you for your attention.
Thank you so much, Davinia. That was great. I think definitely this is, non-invasive therapy is really something that clinicians are looking forward to because it's much more easy to implement. It's really the type of thing you can do at the bedside. So it's really something that, will most likely be integrated first before we have other things like ultrasound and things like that we're working on. But I just wanted to acknowledge the fact that indeed working with controls is very important, but it might be challenging too because even though it's a healthy brain, it has its own functioning that is very distinct from the population you're targeting. And sometimes you might have surprises where, maybe you don't want to increase the activity of the thalamus. Maybe there is too much activity in the thalamus. Maybe you should inhibit a little bit. So I think that, there is most likely subgroup and subpopulation where you are talking about CMD. Might be that in CMD that's different than, in minimally conscious state, for example, where this technique has shown really some good efficacy and might work very well for that kind of model. But CMD might be slightly different. So that's very interesting to actually have that distinction between those two groups because they indeed might benefit from the therapy in different ways. So it's very interesting. I think that there are, if people have questions, I have questions on my own, but please, I don't want to be the only one to ask question here. So if you have question, go for it. I have a question from Judith Allenson that you might know. Great talk. How long did the increased activity last in the 20 years old man after stimulation?
Yeah, that's a great question. And so hi, Judith. So I think in the case of this patient, obviously, because we were stimulating daily for 5 days, so we have those increases consistently on that. So in the kind of behaviors never went back to baseline from one day to another, but obviously the stimulation was coming back the next day, within 24 hours. Once we stopped the stimulation, the patient went back to baseline relatively quickly. And I think this is really, really important because I think what my take on this, and particularly around CMD, is that the stimulation itself is not what's going to help the patients get better. And my take on this is that if the patient is not able to engage in rehabilitation because they're unresponsive, but you make them responsive, what you're doing there is you're opening the door for all the beautiful therapists that have lots of evidence in terms of how to rehabilitate patients with brain injury. So then maybe we put the patient in a condition where we can do formal goal-oriented rehab, and then that's what's going to lead to the long-term kind of changes in the trajectory of the patients. Of course, I have no data to back that up, but that's where I'm coming from with this intervention.
Yeah, and I think too, Judith, you have another question?
Only if I don't want to hog things, but I just wondered, because I know you're waiting to get a formal grant. Are you going to put chemical interventions in to perhaps help things persist, is what I was wondering. One of the dopaminergic things or whatever.
Yeah, so at the minute, the challenge that we are facing with that is that because many of those are indicated anyway, and they're being prescribed anyway, is very tricky to then interfere with that. So the way that we're doing it from the point of view of the ethics around the study is that even, I mean, we wait until patients are stable and the assessment has happened and all the conversations about end of life, etc., have taken place, etc., even before we kind of start intervention. So at that point, the medication is somewhat stable. But if at any point the clinical team decides that the patient is going to go on whatever chemical agent and they're taking part in a study, it doesn't matter. If it's clinically indicated, they go into that. So that's the difficulty here, to try to kind of enter that as a condition that we have control over. But yeah, I think it'd be very interesting to do.
There's
I think
another
next
question,
time.
two other questions actually. Sorry, Judith.
Yes.
So Anna Estraneo is asking, saying first, great talk, thank you. And she asked, the ethical issue remains open, treating patients with tDCS plus mobilization only in those identified as having CMD raised concerns. Could this intervention not also be effective in other non-CMD patients, anoxic VS, in whom bilateral thalamocortical disconnection are likely present?
Yeah, that's a great question. And that's what we're doing. I think I wasn't clear enough. So the kind of mechanism and the patients that we think are going to be most likely to benefit are those who have CMD. Now, CMD, now we don't talk about covert awareness in the kind of paradigmatic case of vegetative or UWS and then covertly aware. It's more of a spectrum, isn't it? It just means that some people have a little bit more cognitive function to what they show behaviorally. And this can exist across the board, because you can have an MCS minus patient that is also, showing some command following in the scanner, right? So we don't exclude patients on the basis of being able to detect or not detect CMD. So we're testing it in everybody. We have a sample that is not large enough for us to be able to make group comparisons at the minute about whether this is only indicated in CMD patients or not other patients. But we take patients of all etiologies, all diagnostic levels, and CMD, not CMD status. So that would be something that we do if we have a large enough sample that we can test empirically. But yeah, we're at the minute, and it could well be that this is beneficial for other patients, absolutely.
Aurore has a question. Ooh, the experts. Okay, so great and fascinating talk for the tDCS passive mobilization study. Was the task asked to the patient, motor imagery and behaviorally the same as the passive mobilization? Have you also thought of trying tACS? Yes, beta over M1.
Yeah. So to the first question, yes, it's identical to the healthy participants. So we do get tennis because that's the one that we have the kind of more data in terms of comparing it with earlier results. But then we ask them to move the thumb, to actually physically move the thumb. The only difference is that because we're collecting this data in a clinical hospital, we don't have a way to measure the actual produced movement by the patient in the scanner. So we only have the imaging. But the imaging is in the try to move, not imagine to move. So in that sense, it's the same thing that we're asking the health to do. And the passive mobilization is identical between healthies and patients. But in the healthies is a robotic arm connected to a pneumatic pump that's sending some. It's a bit of a complicated design. In the patients, we have a person in there actually kind of. So then, if they feel some resistance, they can stop, etc. In terms of tACS, yes, we have thought about it. We have no data with this though. It is something that we're thinking at the beginning, and when we were going between tDCS, tACS. And to be perfectly honest, because my background is from imaging, from MRI, and a lot of the evidence that we have in the coupling, we seem to have better evidence that in terms of being able to draw conclusions from the tDCS to the bold response versus tACS with electrophysiology. So that's kind of what based the decision to go for tDCS. But now that we're doing a lot of EEG studies as well, that's definitely something that we're thinking. We haven't done, but yeah, considering for sure.
I have Fatime Zevzadeh, who is asking a question too. Very interesting. Thanks for the talk. I might have missed, but did you also see improvement in behavior in patients with increased brain activity?
Yeah, so you didn't miss. I just didn't talk too much about this because we're kind of getting the paper, because we're still trying to figure out how to best interpret these results. So, but what I can say is that we have different levels. So we have patients who have changes in behavior and in brain activity, but we also have a group of patients who show changes in the brain activity but not in behavior. So, of course, you can think about this and interpret it. Maybe there's some early changes that are not yet strong enough to manifest themselves as behavioral changes, and that could be the first thing that comes to mind. But this is something that we're kind of trying to think about. I think something important as well to mention is that when you're talking about behavioral improvements, these are really tricky to kind of pin down, because as you know, that there's evidence, and this has been characterized beautifully recently by Jacina's team and others in terms of the fluctuations that you see across the board, right? So if you see a change, if you only measure before and after and you see a change of 1 point in CRSR, does this mean that it worked, or you just happen to capture a fluctuation? Who knows? So we have assessments every day, and we have, at the beginning, we were doing assessments immediately after tDCS and 1 hour after. Until then, the therapists got sick of us. Like, you can't ask us to do this much. So we kind of reduced it a little bit. But we do have that. And when we're talking about improvements, I'm looking at it more in terms of what are the fluctuations and what is the variability during that week, rather than like this pre versus post, which is very helpful, but it's difficult to interpret, I think. So this is just to say that because we have so much data, it's quite complex, and we're kind of trying to figure things out because there's a number of ways in which you can look at the data.
Thank you so much, Davinia. We'll stop here. If you have any question, you can send an email to Ginger, myself, or Aurore to get the email of Davinia. That's complicated. But like that, you have your question answered. We'll organize another webinar in 2 months or so, in April, most likely beginning of April. I will keep you posted on that. And I just wanted to remind you that there is the NABIS, or rather the Brain Injury Summit that is in March from the 9th to the 13th in Washington. So look it up if you want to go and attend. There is also the International Pediatric Brain Injury Society. It's the 6th Biennial Conference on Pediatric Brain Injury, and it will be in April, at the end of April. And it will be organized in Calgary, Alberta, Canada. So you can look that up also on the website. But thank you so much, Davinia. It was extremely interesting. I think that attendee will definitely find it very helpful. And of course, there will be a lot of follow-up regarding that kind of field, I'm sure, with both Davinia and Aurore as experts, and it will be very exciting to see your publication soon. We can wait. Okay, thank you so much, everyone, for attending. I wish you a wonderful night, evening, or day, and I will see you in 2 months, and we will see you in 2 months. Okay.
Thank you.
Bye, everyone. Bye-bye. Bye-bye.